This is multivariable calculus, and in this video I'm going to talk about section 15.8, triple integrals in cylindrical coordinates. And the big thing about this, and really these next two sections, we're going to talk about triple integrals in cylindrical coordinates and then the same thing in spherical coordinates. We're going to be looking at the exact same types of problems that we've been doing, some where we're just going to solve the triple integrals, and then some basic application problems. But it's generally the same idea as what we were doing before, just using a more convenient coordinate system to set up the problems. So we talked about this a lot back in section 15.4, I believe it was, when we talked about double integrals in polar coordinates. So triple integrals in cylindrical coordinates is a pretty easy transition from the double integrals. We already talked about the idea of converting your functions when they're in terms of x and y over to be in terms of r and theta. And so a lot of this is going to be the same. The only difference is now we have a z coordinate to work with as well. But we've done cylindrical coordinates early in the year, and we've worked with polar coordinates recently, so this should be a pretty easy transition. So what we're doing here is we're really looking at setting up triple integrals when we've got situations where equations that are representing our bounds are typically going to be more easily described in a polar form or a cylindrical form. Okay, so the setup for these is generally the same. The only big difference is when we convert our equations from being in terms of x and y and z to being in terms of r and theta, we just have to remember that we are multiplying by that r. So remember, we convert the function over in terms of r and theta. The z doesn't change in cylindrical coordinates, but the x and the y get written in terms of r and theta. And then remember, we have to multiply by the r. And we talked about that previously, about why that r shows up. So that is something you're going to have to do when you convert these over. But notice our limits of integration. We're actually going to always integrate in the same order here. We're always going to integrate with respect to z first, and then respect to r, and then with respect to theta. So it's generally pretty simple because we have kind of the same setup that we're going to use every time. Okay, so if you notice, before when we were doing triple integrals, we were essentially adding up a bunch of small rectangular prisms, and that's what the triple integral was doing. Well, now we've got the same idea here. This is just representing one of our small differential pieces. We've still got sort of one of these, I guess you could call it like a cylindrical prism that we're looking at here. So it still has sort of the same idea where we've got the three dimensions, but one of those dimensions is r d theta. Okay, so let's take a look at how we can use this. And we've seen actually a couple of problems you might have noticed back in section 15.7. There were situations where it might have been a little bit easier to work them in a cylindrical form. So this is one where it definitely makes more sense to work it in a cylindrical form. And what we've got is a problem where they've given us a diagram here, but it says use triple integration in cylindrical coordinates to find the volume of the solid G that is bounded above by the hemisphere. Z is square root of 25 minus x squared minus y squared, below by the xy plane, and laterally by the cylinder x squared plus y squared is equal to 9. Okay, so you can see the figure here. Now, these problems where they're going to be more difficult is when you're not given these figures. But typically you are going to be given them. But when you're not, you either have to be able to visualize it, or you're going to want to graph them using a 3D graphing system. Okay, so I'm looking at this in a three-dimensional sense. And remember, we're always going to integrate with respect to z first. It's pretty clear here that my z is going to be bounded between 0 and the square root of 25 minus r squared. Now, if I look at the rest of this, when I'm looking at my r and theta values, since I have this circle here, it's pretty clear my r values are going to be bounded between 0 and 3, and my theta values are going to go from 0 to 2 pi because I'm going all the way around the pole. Okay, so knowing that to be the case, this is actually fairly easy to set up. So the main thing is, what order am I going to integrate in? So I'm going to put in my triple integral here, and then we'll just fill in the limits of integration. So since we are finding the volume of this, we're going to start with r dz dr d theta. Okay, so that's going to be my kind of general setup. Now, I want to think about, I'm integrating with respect to z first. What are those z limits of integration? Well, we already mentioned the lower bound is 0. The upper bound would be the square root of 25 minus r squared. Now, notice that this conversion's already been done for you. We have to remember the conversions that we talked about when we did polar coordinates and when we did cylindrical coordinates earlier in the year. When I see an x squared plus a y squared, remember that's an r squared. So you see the same thing over here where we had x squared plus y squared is 9. That means r is equal to 3. Okay, so my next set of limits of integration are going to deal with the r values. So clearly that goes from 0 to 3. And then for the theta values, I'm just going to go from 0 to 2 pi. All right, so at this point, I really just have to solve this out, right? It's not really anything different than what we've done before from a triple integral standpoint, except for the setup. So now when I solve this out, I'm not going to go through all the steps on these, just like I've mentioned in these most recent videos. You guys can solve these pretty well from here, but I just want to point out a couple of things. So let's say we solved that inside integral, and so we would get RZ as the antiderivative and then plug in our limits of integration. A lot of these are going to be pretty simple, and you can skip a lot of these steps. And when you can, I'm fine if you can do, like, for example, r dz from 0 to square root of 25 minus r squared. If you can do that in your head, that's totally fine. What we would end up with here is r square root of 25 minus r squared dr d theta. Okay, so now we've got it down into a double integral in essentially polar coordinates now. And this is exactly what we did before. So remember, when we had problems like this, in a lot of cases, you can break these integrals apart. You can work the r integral, you can work the theta integral, and then just multiply the results. Or in this case, it's pretty clear I can solve the r integral and multiply by 2 pi. So use the little things you can to save yourself time to solve these out. We're typically going to look for exact solutions, but not always. So depending on whether or not you need an exact solution on this problem, we could very easily plug in the integral from 0 to 3 for r squared of 25 minus r squared dr. We could plug that into the calculator and get an approximation, multiply by 2 pi, and we're done. So when needed, solve them by hand. When it's not needed, you can plug them into the calculator once you get down to that double integral. So in this case, if I were to solve this out, my volume, the exact value is 122 pi over 3. Okay, so not really that difficult to do. The one big thing when you set these up, don't forget about that r, just like when we were doing the double integrals with polar coordinates. Okay, so again, relatively simple here because the diagrams were already given. Okay, so now this is just going through just a reminder. When we convert, don't forget when you have a function in terms of x and y and z, when we convert over, the x's and the y's are going to be written in terms of r's and thetas. So x is r cosine theta, y is r sine theta. Okay, so here's one where we're going to convert. So let's say, maybe back in section 15.7, we had worked a problem like this, and we set up and got these kind of ugly limits of integration. Well, what we can do now that we know how to do these with cylindrical coordinates is we could convert this and make this into a little bit simpler problem. Rather than dealing with the square roots and the 9 minus x squared minus y squared, I can convert this over into a little bit simpler problem. What I want to be thinking about here is essentially, what do all these things represent? So based on the z limits of integration, I can see that I've got a function that is bounding. I'm at z is 0, and then I've got an upper function that's bounding me. And then I can also look at the y limits of integration and see that I'm looking at a circular region. And then same thing from the x limits of integration. I can see that I'm looking from one side of the circle to the other. So if you can interpret what's happening geometrically, it makes it pretty easy to convert these things over. So I'm going to rewrite this as a triple integral in cylindrical coordinates. Okay, so first of all, x squared is going to become r squared cosine squared theta. Also, when I convert my integral, don't forget we have that extra r that we have to throw into here. So we're going to put in r cubed cosine squared theta. And that's going to be same differential here, dz. But now we're also going to have dr d theta. Okay, so we got the R. Remember how that showed up. And now when we look at the Z limits of integration, since we're now working in cylindrical coordinates, we're going to want to write this as 0 to 9 minus R squared. And then for the R values, we're going to want to go from 0 to 3. And for the theta values, I'm going to go from 0 to 2 pi. So we've got to be able to recognize that in the XY plane, we're dealing with a circular region, and that allows me to come up with these R and theta limits of integration. Okay, so from here, a little messier to solve this one, but still not terrible to solve it out. If I were to deal with that Z integral, I'll just show you the inside integral, and then we can talk about the rest of it. So I've still got this integral from 0 to 2 pi, and then the integral from 0 to 3. But if we solve the inside part of this, when we do the antiderivative with respect to Z, we're just going to get Z R cubed cosine squared theta, and then we're going to plug in 0 to 9R squared, and we're going to end up with 9R cubed minus R to the 5th times cosine squared theta dr d theta. Okay, so again, this is, like when we were dealing with the double integrals over a rectangular region, we just have constant limits of integration. So if we really want to at this point, we can deal with the two integrals separately, or you can solve it as, the R integral embedded within the theta integral and kind of work from the inside out. It's up to you. At this point, when you solve it out though, you would end up with an exact solution here of 243 pi over 4. Okay, so again, relatively simple once you get them set up. The big thing that you have to remember is to multiply by that R. And remember, try to remember why we're doing that. Don't just randomly do it. We talked a lot about why that was the case. Okay, so let's take a look at another problem. It says solid E lies within the cylinder x squared plus y squared is 1. Below the plane Z equals 4, and above the paraboloid Z is 1 minus x squared minus y squared, as shown. Okay, even if we didn't have a figure here, that's one that we should be able to kind of visualize. Okay, now this is getting back into the applications that we had looked at back in section 15.5 and a little in section 15.7. It says the density at any point is proportional to its distance from the axis of the cylinder. Find the mass of E. So we want to find the mass of this object. Okay, so first of all, they gave us a description of the density here. The density at any point is proportional to its distance from the axis of the cylinder. So if I were to write out a density function, well, I've got my proportionality constant K, and the distance from the axis of the cylinder would be the square root of x squared plus y squared. Okay, just thinking in kind of like an XY plane type of direction. So that's how I would find the density at any particular point. Now, if I want to find the mass of this object, since it's a three-dimensional object, we're going to have a triple integral over this region E, and we know we're going to integrate our density. And just as a general setup, we'll just call that dV. Now, again, I can kind of recognize that I probably want to use cylindrical coordinates here because I'm seeing a lot of x squareds plus y squareds, which is indicating to me this would be very easy to convert over into cylindrical coordinates. Okay, so let's think about, first of all, our Z limits of integration. You can see that we've got this paraboloid down below, and then we have Z equals 4 up above. Well, the paraboloid 1 minus x squared minus y squared is the same as 1 minus r squared. So that's really the most difficult limit of integration that I've got to think about. So my Z values are going to be bounded below by 1 minus r squared and above by 4. Okay, and then my integrand here would be K square root of x squared plus y squared. Well, that's the square root of r squared. And so that's going to give me an r. But then remember, we also have to convert over from rectangular into cylindrical coordinates. So we get an r from this, and then we're also going to get our other r when we do our conversion. So I'm going to get my proportionality constant times r squared, and then I'll have dz dr d theta. Okay, so clearly in the xy plane, I'm dealing with a circle again. So it's a circle with a radius of 1. So I'm going to go from 0 to 1 for the r values, and then from 0 to 2 pi for my theta values. Okay, now that I've got this converted over, again, you can see this is relatively simple to solve because I don't have a lot that I have in here that's very complicated from a z perspective. I'm just going to take an antiderivative and get kr squared z, and then plug in my limits of integration, and then the rest of it becomes very simple. Okay, so let's say we solved that inside integral. What we would end up with here is this double integral from 0 to 2 pi and then 0 to 1. And when I plug everything in and simplify, I'm going to end up with kr cubed over 3 evaluated from 1 minus r squared to 4. And let's see, I'm going to say this is from z equals 1 minus r squared to 4. And then we'd still have our dr d theta. So obviously there'd be a little bit of algebra there to simplify that kr cubed over 3 down using those limits of integration. But then we just have, again, really kind of a double integral that can be separated into 2 single integrals that we can multiply together, or just solve the inside integral and multiply by 2 pi since there's no thetas here this time. What you would end up with here for the mass is 12 pi k over 5. Okay, so again, not that difficult to do, and it's kind of obvious in a lot of these scenarios why we would be using cylindrical coordinates. All right, I've got one more problem here that I want you to try. It says use cylindrical coordinates to find the volume of the solid enclosed by the paraboloid z equals x squared plus y squared, and the plane z is equal to 9. So notice we didn't have a diagram this time. Several of your homework problems will be like this. So you either have to be able to visualize this, or you're going to need to plot this using something like GeoGebra 3D. So I want you to take a few minutes. I want you to pause the video, try to set up the triple integral and solve it out. And when you come back, I'll show you the solution. Okay, so you'll notice here in my solution, I didn't really show the triple integral being solved. The most important part here is the setup. I'm assuming you know how to solve the triple integral once you have it. So you can see that the first thing is I have to remember I'm not setting this up in a rectangular form. I'm setting this up in a cylindrical form. So the thing that people tend to forget is that we have to have this r here. So don't forget about that every time we use cylindrical coordinates. So I have r dz dr d theta, and my z values are bounded between z equals x squared plus y squared. That's where the r squared came from. X squared plus y squared is r squared, and then z is equal to 9. And then the rest of this, if I'm thinking about, okay, what's the region that I'm thinking about in the xy plane? Well, I'm just going to set z equal to 9 in this equation. 9 equals x squared plus y squared gives me that circle with a radius of 3. So that's where these values came from 0 to 3, and then 0 to 2 pi, because that's going to take me all the way around the circle from the theta perspective. In the end, you should get 81 pi over 2. Okay, so for these problems, I showed you generally some pretty easy ones. When you work through the assignment, you'll have some that are a little more challenging, but for the most part, you can recognize when you're going to want to use those cylindrical coordinates whenever you see the x squared plus y squared or that type of scenario. In a lot of cases, it's going to be easier to work it in a cylindrical form as opposed to a rectangular form.